When you select K-epsilon models or the Reynolds stress model in the viscous model panel, then you also have to choose a near wall treatment. The choices are standard wall functions, non-equilibrium wall functions, enhanced wall treatment, and there's also an option for user-defined wall functions. With standard and non-equilibrium wall functions, the first grid point needs to be in the logarithmic layer, and so as we saw in one of the earlier slides, this means that the near wall region is not resolved by the mesh, and therefore the near wall mesh is relatively coarse. Wall functions are best suited for high Reynolds number attached flows, and compared to standard wall functions, non-equilibrium wall functions can give more accurate predictions if you have adverse pressure gradient and mild separation, but generally we don't recommend the use of wall functions when you're trying to predict flow separation. The recommended choice for either the K-epsilon or the Reynolds stress models is enhanced wall treatment, which we saw in the slide just before this. Enhanced wall treatment can be used for low Reynolds number flows or flows where anything interesting is happening close to the boundaries such as heat transfer or flow separation. And so generally this requires a very fine near wall mesh that can resolve the viscous sublayer. But we did see on the slide that this can also handle coarse near wall meshes and behave in a wall function kind of mode if the mesh is coarser. So for this reason, the enhanced wall treatment is the recommended choice. As the previous slide mentioned, the only option for the near wall treatment for the SST K-omega and standard K-omega models is the default Y+ insensitive wall treatment. This means that there's no choice to be made in the panel, but even though you don't pick anything in the panel, you still need to choose which meshing strategy that you're going to use. Both the SST and K-omega models are formulated to be near wall resolving models, which means that the idea is for the viscous sublayer to be resolved by the mesh. That means that the Y+ value should be low, but remember that Y+ is not a magic number, and it also means that you need to have a good grid as well as a low Y+. This strategy is necessary if you're trying to accurately predict flow separation. Now both of these models can be used with a coarser near wall mesh, and you can still get valid results within the limitations of logarithmic wall functions. If you choose this approach, the first grid point needs to be in the logarithmic layer. In most cases that means that Y+ should be less than about 300, but remember if the system Reynolds number is very high, then higher values for Y+ are acceptable because the log layer can extend to much higher values outwards than 300. It's important also to remember if you're doing this, although your results may be valid within the limitations of wall functions, many advantages of the SST K-omega and standard K-omega models can be lost if the near wall mesh is coarse.